Hi, in this video we will learn about a form for matrices which will be playing very important role in all elimination methods that we learn for solving system of linear equations. This form is called row reduced echelon form, and let me just tell you what is the definition. A matrix is in row reduced echelon form. Well, sometimes we write it as row reduced echelon form if it satisfies the following conditions. 4 conditions we have. One is that all 0 rows must be at the bottom. So any 0 rows, by 0 rows we mean the rows consisting entirely zeros. So all entries are 0. Any 0 rows is at the bottom. So that's the first thing. The second thing is that, well, if a row is not 0, it means that there are some non-zero entry. The first non-zero entry must be 1. In each non-zero row, well, it means that there are some entries which are not 0. The first non-zero entry is 1. We call such ones as leading one. And if a column has a leading one of some rows, then every other entry in that column must be 0. So in a column that contains a leading one for some rows, all other entries are 0. So the leading ones, everything above leading one and below leading one must be 0 in the column. And the last condition, which is a very important condition, is giving us the pattern in which the leading ones will appear. In any 2 rows with some non-zero entries, with some non-zero entries, so they have leading ones. Basically, the leading one of the higher row is farther away or farther to the left. So it means that, well, if these 2 rows are non-zero rows, the one on the row, a higher row, must be into the left. So it means that we will have step pattern. So I will write when we talked about these ones, I'll write as a step pattern. So these 4 conditions, for example, what are the examples of such matrices. For example, if let's just say you have 1, 0, 0, 0, 1, 0, then 0, 0, 0. This is a row reduced echelon 4. Why? Well, we have 0 row at the bottom. Every row which is not 0 starts with leading 1. So these are leading 1. Everything above leading 1, below leading 1 in the column is 0. Here you see everything is 0. And the important one, that it has step pattern. The leading ones have step pattern. Let's have another one. Something like this one. So we have 0, 1, 0, 0, and then 0, 0, 0, 1. Well, here, so we don't have 0 rows. Every non-zero row starts with leading 1. Those are leading ones. Above and below leading ones are 0 in the same column. So the columns which have leading 1 has everything else 0. And, well, these guys form step pattern. Well, you may say, what will happen here? Well, actually, this can be any number you like, because it is not in the column of a leading one, and it doesn't do anything with the conditions that we have. It can be any number like that. And another one, let me just write another one. Something like 0, 1, 0, 0, 0. We have only one leading one. Everything else in that column is 0. And, well, there's no other thing to form steps, but that's row reduced echelon form. Okay, so we will have to know these things, and we have to be able to work with this. So I have prepared some examples for you. You have to go on these ones and then see how everything works for these examples. Okay, determine why the given matrices are not row reduced in row reduced echelon form. For the first one, you look, okay, the first row is non-zero, and what you notice right away that the first row starts with non-leading 1. So this is why it fails. So it fails because of the condition 2. The other things are all right, but condition 2 fails. How about this one? Okay, so here, the second one, the first row starts, the first non-zero entry of the first row is 1. For the second one, it is, and for the third, it is. How about the column condition? The column condition, below these guys, everything is 0. Below, what? This cannot be 1. So that's why this is not a row reduced echelon form, because the 3 doesn't work. Here, well, we don't have any non-zero entry, so we have these ones as leading ones that satisfy the condition 2. In the column of this last one, there is a non-zero entry, so that is why this is not row reduced echelon form. Even it was 0, again, this is not row reduced echelon form, because you see it doesn't have step-like pattern. So the 4 is also failing here. How about this one? Well, it has 2 conditions. This guy starts with non-leading 1, so that is condition 2. And here the columns are okay, but it is not, again, step-like. So the 4 is not satisfied. It is not satisfied. Okay, so these are the conditions. Let's read a little bit more. Find the values of k for which the following matrices are in row reduced echelon form. Okay, so let's check all the conditions. First of all, do we have 0 rows? I'm talking about the first example. Do we have 0 rows? No, each row has some non-zero entry. That's good. How about the leading one? Yes, each row, each non-zero row starts, the first non-zero entry of each non-zero row is 1. So they're leading ones. And how about the column thing? Well, the column of this guy is all 0. The column of this leading one has k. To this matrix to be in row reduced echelon form, k needs to be 0 because of the column condition, condition 3. And well, we have to also note that these are already in step-like form, so it won't generate anything bad for us. How about this one here in the second one? Well, both rows start with the first non-zero entry is 1. The entries in the columns of leading ones are 0. Very nice. And leading ones are forming step-like pattern. Yeah. So there's no condition on k. So k can be any number. The matrix will be in row reduced echelon form for any values of k. How about this last one? This last one, okay, the first row starts with 1, the second row starts with 1. Well, the first non-zero is 1. The last one has a k in it. If that entry is supposed to be the first non-zero entry, it must be 1. Yes. But when you look, if k is 1, what will happen here is that, let's say k is 1. If k is 1, then our matrix will be 1, 0, 0, 2, 0, 1, 2, 0, and 0, 0, 0, 1. Well, everything is nice. We have the pattern we are looking for, but the column condition is not satisfied here. Everything in the column of leading one must be 0. Here there's a 2, so that means that k cannot be 1. How about 2, 3? Well, it cannot be 2, 3 because everything in this the first entry, non-zero entry of each row must be 1. So everything before k is 0. So if k is going to be non-zero, it must be 1. We showed that it cannot be 1. As a result, the only possibility is that k is 0. So we have 1, 0, 0, 2, 0, 1, 2, 0, 0, 0, 0, 0. This is the only possibility that we get a row reduced echelon form from this matrix. While we are working with matrices, how about augmented matrix? Let me just remark an augmented matrix and augmented matrix. Remember, how are the augmented matrices? We have the coefficient part and then we have the constant term part. Yes, we separate them by a line. Is in row reduced echelon form if, well, the coefficient part is in row reduced echelon form. We just ignore the part B. While doing some work with the matrix, augmented matrix, we apply it on the whole rows, the whole row of coefficient and B. But when it comes to checking row reduced echelon form, we only check the part A. So if A is in row reduced echelon form, that B is tagging along A. So it will come with A wherever, but when we're checking row reduced echelon form, we only check the part A. Very nice. Let's do a few more things. Okay, find augmented matrix in row reduced echelon form, which is row equivalent to the given ones. Row equivalent means what? It means that when we do row reduced echelon forms, we get to that matrix. Okay, so in other words, what this question asks is that do some row reduced echelon forms and turn this matrix, this augmented matrices, to row reduced echelon form. So here we look at these matrices and we notice that, okay, the first thing that we see is that the first non-zero entry of the first row is not 1, so we have to turn it to 1. To turn 2 to 1, we can multiply the whole row 1 by 1 over 2 such that this guy will be 1. So this is half of, no, I don't need to write that. Half of 2 is 1, and half of 0 is 0. Half of 1 is 1 over 2. While we applying row reduced elementary row operations, we have to apply all the way to the end of the augmented matrix. And then the other part is 0, 1, 0, and we don't need to do anything. Now you see, the starting non-zero entry is 1. Everything else in those columns are 0, and we have step-like pattern here. How about this one? Well, the first row starts with the non-zero 1, leading 1, and the leading 1 of row 2 is there. Well, you may say that this is also a leading 1, but it is not, because you see by the condition we have to turn it to 0. Yes, so how can I turn this entry here to 0? Well, if I subtract row 2 from row 3, that would do the job, because I will have 1 minus 1. So it will be, so first row, I'm not touching the first row. The second row, we are not touching. We are using second row to do the elementary row operation, but we are not changing it. And for the third one, this is 0 minus 0 is 0, 0 minus 0 is 0, and 1 minus 1 is 0, and 2 minus 0 is just 2. Now we are in a good shape. This is, you see, the all 0 row is down, the leading ones are step-like, and then we have 0 columns for these ones. You may say, well, how this step is longer than the other one? It doesn't matter what is the length of each step. The step-like pattern should be there. One could be like this, and then this, and so you have to have that step-like pattern. How about this one? Okay, first you see that these are leading 1, and this is kind of leading 1 for the third one, but we have to make sure that this entry above there is 0. To make that one 0, we can do subtract row 3 from row 2. So row 1 I'm not touching, and this is and row 3 we are not touching. We are using row 3 to change row 2, but we are not. And then we are replacing row 2 by R2 minus R3. So 1 minus 0 is 1, 0 minus 0 is 0, 1 minus 1 is 0, and 0 minus 0 is 0. That's nice. Now you look and see, okay, everything looks okay, but the steps, this is not good steps. We have to turn them to steps. To turn this guy to row reduced echelon form, we need to apply this interchanging operation. If we interchange row 2 and row 1, we will have this guy. And this will be row reduced echelon form. And the last one, well, First, this is leading one good, but since it needs to be further in the left, we have to bring it up. So R1 and R2 we interchange. So 1, 0, 1. You see, when I'm applying the elementary row operations, I apply all the way through the constant part also. 0, 3, 6. Now, this is leading one. It's in the right place. Everything in that column is 0. Now we move to the next row. This is the first non-zero entry. First non-zero entry must be 1. But this guy is 3. We have to turn it to 1 by multiplying the whole row by 1 over 3. So it will give us 1, 0, 1, and 0. 3 over 3 is 1, and 1 over 3 times 6 is 2. That's how we go from there. Well, we will study this kind of operation in details very soon in another video. But for now, these were some examples, basics of row reduced echelon form, if a matrix is in row reduced echelon form or not, or what we can do to turn it into row reduced echelon form.